Welcome to AP Chemistry and welcome to your first lecture for AP Chemistry. This is a lecture based on Chapter 1, Chemical Foundations, Zumdahl 10th edition. You should probably read pages 1 through 31 to get Dr. Zumdahl's take on this material as well. He does an excellent job explaining things. And I will attempt to go through and hit the high points. I'm Mr. Koker, and this is AP Chemistry. The chapter starts out with an overview of what chemistry is. Chemistry is the science that's going to talk a lot about matter. What is matter made of? What is the composition of matter? And short answer to that question, of course, would just be that matter is made of atoms. Atoms are central to understanding chemistry. Atoms, groups of atoms put together with covalent bonds called molecules, atoms that have lost and gained electrons called ions. These are the basic particles that we talk about in chemistry that matter is made of. Atoms are complex structures. You'll learn throughout the year about the structure of atoms. With just very few atoms, about 100 atoms, everything in the universe that is here is formed. And so all the different varied and unique materials in the world are in fact combinations of atoms. And as we learn about their complex nature and how they fit together, we'll learn more about matter. Atoms are generally what you'd consider submicroscopic. Microscopic means you have to use a microscope to see it. The kind of microscopes that you had in biology class would not work for seeing atoms. And so atoms are submicroscopic. Now we do have, in the last 30 or 40 years, been able to get some brief images or fuzzy images of atoms. One particular instrument that can see down to the atomic level, or rather feel down to the atomic level, is an STM, a scanning tunneling microscope. You see an artist's rendition of a scanning tunneling microscope in the lower left-hand corner of this slide. In that picture, you see a probe coming down. The probe is atomically sharp. It has one atom on its tip, and it's going to scan across the surface of an atomically flat piece of material. And as it scans, it detects the very faint electrical fields that those atoms below it are forming. And as a result, it can read or feel the surface of the material, even down to the size of an atom. And so that's how a scanning tunneling microscope works. It scans across the surface, and a computer will generate an image of what that probe is feeling below the surface of the probe there on the surface of the atoms. And so we can see down to the atomic level with such very highly advanced machines. I was fortunate enough when I was getting my master's in material science, one of the lab experiments I did as part of a class was actually getting to use a scanning tunneling microscope, and they are really cool instruments. Now, generally, most of the chemistry that we know does not come from using scanning tunneling microscopes. We are able to determine a lot of chemistry from indirect methods, particularly from macroscopic observations, by looking at the behavior of matter on the macroscopic scale, or the scale of chairs and computers and people, and the scale that we can see with our eyes. We can actually determine a lot about the atoms that make up things. It does require quite a bit of interpretation, and that's part of the fun of chemistry, is being able to look at the macroscopic world and think about what's happening submicroscopically. So do we need an STM to know that atoms exist? No. back in the early 1800s. John Dalton theorized the existence of atoms, and that theory um, has served us quite well. We don't need an STM to know that they exist, but an STM does verify it for us. There's about 100 different kinds of atoms, but there are millions and millions of different kinds of compounds and ionic crystals and organic molecules. So these atoms fit together generally in whole number ratios and make these various compounds that we study in chemistry. So two of the fundamental things that we keep in mind as we study chemistry are that matter is composed of various types of atoms. The different types, of course, are listed on the periodic table. And that one substance can change to another by reorganizing the way the atoms attach to each other. It doesn't change one atom to another, we simply reorganize the way they attach. It's very much like taking some Lego creation that you've made and take it apart and put it together a different way to make a new Lego creation. In the same way, we can take atoms apart from each other and put them together with atoms in a different way and make new compounds. Science is this process that we use to understand nature and its changes, and particularly the nature and changes of matter are the particular science of chemistry. Science is a way to solve problems. We use a particular approach, a method, a scientific method, a logical approach. We make observations, which is collecting data. We can collect qualitative and quantitative data. And then we take that information that we observe in the real world and we ask ourselves, now what could explain this behavior? What must be happening? Obviously, in chemistry, one of our explanations was that atoms were existing at the submicroscopic level and that these atoms were in fact causing the behavior of macroscopic matter. We call that formulating a hypothesis. Then our hypothesis is tested through various experiments to see if the hypothesis stands up to the tests that we make in our experiments, in our research. So we research our hypotheses by testing them in the laboratory or in the real world, and then if those tests continue to come back with the expected results, then we begin to trust our hypothesis. So we call that testing the hypothesis. So if you think about chemistry as a way of solving problems, then really chemistry is going to give you skills outside of just a chemistry class or a chemistry laboratory, but skills in being a better problem solver. So being able to take problems, dissect them, solve them logically, this is something that can help you in not just a chemistry class, but also in life as well. So what is this scientific method? The scientific method is the science, is the framework that science uses for gaining and organizing knowledge. There's a lot of scientific knowledge that man has been able to build up over the past few hundred years. And that scientific knowledge, of course, has gained us the opportunity to create a lot of technology in our world and do a lot of amazing things that people 300 or 400 years ago couldn't even imagine. Cell phones, cars, going to the moon, all these things that science has brought us has come about because we have learned as much as possible about the world around us. So science is this framework that we use for gaining that information. Now, there are many ways that scientists kind of proceed to gain knowledge, but the diagram to the left sort of shows a general way that is kind of a general way of describing the way most scientists think. I'm not saying that everything that's ever discovered in science has to follow exactly this strict pattern, but it is a way of kind of understanding how scientists think. Scientists, of course, think by making observations. Now, you think observation, you think seeing something with your eyes, but this could be detecting something with an instrument. It could be sound. It could be any way in which we can bring information into our observations. Qualitative observations. Sulfur is yellow. Quantitative observations. Water boils at 100 degrees Celsius, or the mass of the sodium chloride in the container is 1.25 grams. These would be quantitative if they involve numbers, qualitative if they don't. Based on those observations, we want to then try to come up with ways of explaining why those observations occur that way. So we call that formulating hypotheses. Then we perform experiments to test those hypotheses, and our experiments and our observations lead us to, well, two things. First of all, we want to be able to summarize our observations. If we summarize our observations and state what kind of pattern we see in our observations, we call that a law. One law of chemistry is Boyle's law. Boyle found that if you double the pressure on a gas, that it will cut the volume of the gas in half. And so he developed his Boyle's law that had to do with how pressure affects volume of a gas. Now note that a law does not explain anything, it simply describes the behavior of the matter as chemists are able to summarize it. So to the better ability we have of making the observations and actually accurately measuring things, we can develop these laws. A theory is actually a statement that is attempting to explain that behavior. So a law is how does matter behave, a theory is why does it behave that way. So a theory, or some people call them models, these are man's attempt to bring order to the universe by explaining why the universe works the way it does. Much of chemistry is explained by the existence of atoms and understanding how they bond together. Now, based on your theory, you should be able to make predictions about the behavior of matter in the laboratory or in the real world. Those predictions can be tested with an experiment, and if the experiment shows that your particular theory, your explanation was not quite right or was totally wrong, then you can modify your theory as needed, or you can even scrap your theory and start over. Theories are simply something that we want to then refine and improve or replace as needed to explain more and more experiments that we're able to do in the laboratory. Robert A. Millikan, in his Nobel Prize acceptance speech, talked about theory and experiment as being the 2 feet that science walks forward on. We have a theory, we come up with a new experiment to test it. The new experiment helps us modify our theory. Our new theory, we develop an experiment to test that. That new experiment helps us, so it's sort of like putting one foot in front of the other, and as we do so, we walk forward in science. Now, it's important to realize that this sounds like, it really takes the human element out of it and just keeps everything completely logical. But in fact, science has many, many examples of how human foibles and human tendencies have affected our understanding of science. Excuse me. Science is not linear. It advances in spurts. It may be affected by outside influences. Politics, because politics often can affect what particular science gets studied. If you think about JFK and his speech on we have decided that we want to go to the moon in the 1960s, that particular political statement in fact had a huge impact on the space program in the United States in the 1960s because everybody was working hard towards the vision that the political leader had put out there. If you think about religion, Galileo was was forced to recount his theories about the organization of the universe, because in religious circles they believed that Earth was the center of the universe, and so um, religion can affect science. War can affect science. The Haber process was actually developed for the purpose of creating explosives for Germany's World War I efforts. In fact, it then became a process that could easily and cheaply develop fertilizers. And so the Haber process actually has helped feed our burgeoning population in the 1900s and 2000s because it was actually developed as a result of war. A couple of good examples of sort of the human side of science might be if you want to Google Ira Remsen and his nitric acid story, or if you want to Google the Haber process, that's another good one to look at the human side of science. Okay, our quantitative measurements are our quantitative observations are called measurements, and there's two parts to any measurement. There's a number, and then there's a scale or a unit. 4.53 grams. You get the number 4.53, you get the unit of grams. We have internationally a fundamental SI, or fundamental international system set of units. It is always better in science to use one set of units and not multiple sets of units. The English system and the metric system, of course, have competed over the years. It's caused a lot of problems. It's better for science if we stick with one system. So the international system of the metric system is the choice of scientists. Volume in science, in chemistry and science, is a very important concept. We talk a lot about the volume of liquids and the volumes of solids, the volumes of gases. So if we take volume, volume is actually connected back to length. Volume is length times length times length, or length times width times height. Volume is length units to the third power. So a cubic meter will actually have 10 decimeters by 10 decimeters by 10 decimeters, which would be 1,000 cubic decimeters. A cubic decimeter, a decimeter is about the width of your hand, is called in the metric system a liter. And so you hear a lot in chemistry class liters and milliliters. A liter is a cubic decimeter. So you see that it's actually connected back to the meter. It's 1/10 of a meter by 1/10 of a meter by 1/10 of a meter. Now if we go even smaller, cubic decimeter, since it's 10 centimeters by 10 centimeters by 10 centimeters, equals 1,000 cubic centimeters, or cc's if you're a doctor. 1,000 cubic centimeters would be the same as 1,000 milliliters. And so the milliliter is connected to the centimeter, which is connected to the decimeter, which is connected to the liter. So we see that all these units connect to each other. But length to the third power is volume. So volume is an important concept if we're talking about matter. Mass is another important concept if you're talking about matter. We often mix up mass and weight. Weight is actually the force that gravity exerts on mass. We often use weight to measure mass. By putting something on a balance, you're using its weight to measure its mass. You're using the pull of gravity on that object as it compresses a spring in the balance. That is then used to measure the mass. But the technical definition of mass is the resistance of an object to change its state of motion. All mass has inertia. So even if a particular piece of mass was not on Earth and not affected by gravity, it would still have a resistance to its motion. All matter is at rest or in motion and wants to stay at rest or in motion. We call that inertia. If you look at the chemical connections, page 10, you'll see an important little reading there on the importance of units. So on this page here, you'll see that we have the metric prefixes and what they stand for. We talk about measuring, like measuring volume in cylinder and measuring the meniscus, the bottom of the meniscus. You probably remember that from your earlier chemistry classes. We show some different objects for measuring volume, such as the volumetric flask on the left here, the burette, the graduated cylinder, the pipette. We also have a list of the 7 fundamental quantities and the 7 units used in the SI system. For length, we use meter or M, mass is kilogram or kg, time is second or S, electric current is ampere or amps, and that's capital A, temperature is kelvins or K, amount of substance is moles, and luminous intensity is candela. So we take and we invent these instruments for measuring, but we have to realize that instruments are made by people. People cannot do things perfectly. We can't measure perfectly things that we measure in lab. And so all measurements are going to have some degree of uncertainty. In fact, one of the fundamental ideas of science is that just the act of measuring something can affect the thing you're trying to measure. So measurements have some degree of uncertainty. The precision of your instrument is going to have a big effect on the degree of certainty that you have for your particular measurement. So in general, if our instruments are not digital, see, if it's digital, you simply write down the digits that are showing on the screen. So like a balance or a digital thermometer, you just write down the digits. But if our instrument is not digital, if it's a ruler where we're reading marks on the ruler, or we're reading the marks on a graduated cylinder or a burette, we always try to estimate the last digit. So in other words, we try to read between the lines what that last digit is. And so if it's halfway between the line above and the line below, we take that as 0.5. So if I have a mark for 1 milliliter and a mark for 2 milliliters and it's halfway between, I would call that 1.5 milliliters. These measured digits, including that last digit that's estimated, there's always some uncertainty in that last digit. These measured digits are called significant figures. Typically we say that the last digit could be plus or minus 1. So my eye says it's halfway between 1 and 2 milliliters, so I'm going to call it 1.5. But my eyes could be a little bit off, and it could be 1.6 or 1.4. So as you see measured numbers with units labeled and listed in data tables, you can assume that the last digit was estimated to be plus or minus 1, that value. So what's the difference between 25 milliliters and 25.00 milliliters? Well, it's the degree of precision. 25 milliliters could be 26, could be 24. It's got a lot more variability to it. But 25.00 milliliters has been measured with an instrument that probably had marks to the 10th of a milliliter, and then you read between the lines to get the 100th of a milliliter. And so you were actually somewhat confident in the volume of 25.00 milliliters all the way to the 100th of a milliliter. You're only confident on 25 milliliters to the 1 milliliter. Accuracy is a term we use in describing uncertainty in measurement. It's actually the agreement between the measured value and the true value, assuming, in fact, that you know the true value. This is measured by a quantity called percent error. Percent error is when you compare the measured value and the true value to see what percent off you are from the true value. So to get the answer to within 1% of the true value means that you've gotten it plus or minus 1%. Precision and accuracy are often used interchangeably, but they shouldn't be. In fact, they have a difference in their definition. Precision is actually how well you can repeat, or what is the degree of agreement between several measurements all measured the same way. And so if you're sent to lab to measure something and to measure it multiple times to be sure that you're getting it right, that's what we mean by precision. There's actually a statistical calculation called standard deviation that we use to measure the degree of precision. So how well were you able to repeat your results? If results are not repeatable, then you can't really trust them very well. So we have two kinds of error that can occur. One is called random or indeterminate error. That's actually just due to the precision of the instrument. Random error is just as likely to be high or low. That's why we estimate that last digit to be plus or minus 1. Random or indeterminate error just comes from the fact that measurements can't be made perfectly. Systematic error or determinate error is when your error is always in the same direction. If you're doing a measurement, but you are always getting the answer to be 1 gram too high on the mass, that could be simply the calibration of the instrument. So if you have an incorrect technique, you're not looking at it at eye level, or you're not using the instrument properly, you're allowing air bubbles in it or something, that can create a systematic error so that your volume or your mass is always too high or too low. Also, the lack of calibration for the instrument. If the instrument is not calibrated properly, it can't give you the right answers. So random error just comes from the fact that all errors have measurement, but systematic error comes from something that is actually incorrect about the way you're using the equipment or the way the equipment is giving you the answer. One way we try to get rid of random error is by taking multiple measurements and then averaging those measurements to minimize random error. So by taking the same data 4, 5, 10 times and averaging it, you can get a better answer. You might want to look at example 1.2, page 14, to practice the idea of uncertainty in measurement. Now, significant figures then creates issues with how we are going to perform calculations on the values that we measure in lab. So let's start by, since the number of significant figures will affect the number of significant figures in our answers, let's start by getting the rules down for what is a significant figure in a measured value and what is not considered a significant figure. I'll start out by saying if your numbers are in exponential or scientific notation, there's an easy way to tell that the number of significant figures. It's the part that goes before the times 10 to the power. So if I have 1.62 times 10 to the 7th, the 1.62 are my 3 significant figures. Now, if your number is not listed in scientific notation, then another way of looking at it is non-zero digits are always significant. We always consider non-zero digits to be measured values. People just don't make numbers up out of nowhere, so non-zero digits are significant. The question becomes in the zeros. Leading zeros are not considered significant. Now, what is a leading zero? 0.000056. The zeros in front are leading zeros. Their only purpose is to let you know where the decimal goes. They weren't measured digits. The number wasn't large enough to have anything in those place values. So leading zeros are not considered significant figures. Captive zeros, or zeros trapped between non-zero digits, 101, 101 has a captive zero. The captive zeros are always significant. And then trailing zeros, zeros at the end of a number. 567,000 has 3 zeros at the end of the number. Trailing zeros are significant if there is a decimal showing in the measurement. So 4.200, the 2 zeros after the 2 would be considered trailing zeros. There's a decimal, and so they are considered significant. Generally, if there is no decimal showing in the number, we consider trailing zeros to just be placeholders. So like 567,000 meters, we assume that the zeros were not actually measured, but really are just placeholders. So non-zero digits always significant. Leading zeros not significant. Trailing zeros only significant if there's a decimal. And then we have these numbers that are exact numbers. So be aware that not every number you use in a scientific calculation is actually a measured value. Some of them just come from counting. So for example, if I'm finding the average of the class and there's 22 AP Chem students in the class, I add up all the scores and divide by 22. The 22 was perfect. It's an exact number. It's not that, well, there could have been 23 students or 21 students. I'm good enough at counting to count exactly 22. And so there's no error in that measurement. There is no uncertainty in a counted value. Also, there are certain numbers that are defined. If you think of 2 pi r being the circumference of a circle, the 2 in 2 pi r is a defined value. It's not that 2 pi r only has one significant figure in the 2 value. It's actually exactly 2 because of definition. So if you have exact numbers, they have infinite number of significant figures and will not have any effect on your final calculation as to how you round. Now, let's solve the problem of I measure things in lab. I only have a certain number of significant figures because of the limits of my measuring instrument. So now, well, how many significant figures do I show in my final answer, which is calculated from those measured values? So these are the rules for calculating with measured values that have limited number of significant figures, and then we have these calculators that are going to give us lots of decimal places, so where do we round it off? So it's all about how do I round off my answer based on the number of digits in my measurement. We have two different kinds of rules, but they're both based on the general principle of weakest link. Anything that you have for an answer can only be as good as the weakest link, or the number that was used to find it and how many significant figures it had. So for multiplying and dividing, the number of significant figures of the answer should be the same as the number of significant figures of the least precise input. So if you take a number with, let's say I'm finding a density, and my mass has 2 significant figures, but my volume has 3 significant figures. Well, the mass is actually the weakest link. It only has 2 significant figures. So when I divide the mass by the volume to get the density, I should only show my answer rounded to 2 significant figures, because the mass determines the number of significant figures in the density. Now for addition and subtraction, your result should have the same decimal places or place values as the least precise input. So if I'm trying to add 2 volumes together, one volume measured to the 10th place and one volume measured to the 100th place, the 10th place is my weakest link, and so I should have my answer only to the 10th place. But I do round it. I round to the 10th place. So I look at the number in the 100th place and use that to round to the 10th place. Now the rules for rounding is that we should first of all not round until after all the calculations have been done. So we kind of have to keep track as we do each step as to how many digits are actually significant figures and how many are simply kept in the calculator. But when we get to the end, we're going to round off our answer to the appropriate number of digits based on the rules for sig figs in mathematical calculations. But it's best to carry those extra digits and not to round after each step. So in other words, keep the number in your calculator without rounding until you get to the final answer. So if you're at the final answer and you know that you need to round off to 3 significant figures, you would look at the 4th digit in your answer, and if it's less than 5, then round the 3rd digit to the same number. But if it's more than 5, you're going to round the 3rd digit up. So 2.456 rounds to 2.46, 2.453 rounds to 2.45 if you're trying to round to 3 significant figures. Try the 2 examples in Zoomdoll and practice using your sig figs in calculations with examples 1.3 and 1.4. So if we just think of problem solving in general, we have a general approach that we try to use for solving problems inside chemistry and outside of chemistry. First of all, what is my goal? And that is usually defined by the problem. If it's a word problem in chemistry, The problem determines what is my goal. So read the question, read the question, read the question. What is the question asking for? If you fully understand what the question is asking for, often the approach to solving the problem can become more obvious. How many times maybe have you tried to answer a question on a test, gotten it wrong? When you get the test back, you say, oh, I didn't understand what the question was asking for. I knew the answer, I just didn't understand what the question was asking for. So that's why one of my mantras in chemistry is read the question, read the question, read the question. Make sure you understand the question before you start trying to solve it. So then you look at the question, the problem, and you say, okay, I know what I'm looking for now. What do I have to begin with? What information do I have? What is my current understanding of the information of the problem? So make sure you are fully aware of all the information embedded in the problem or everything that you know to start with. Once you know where you're starting from and what your goal is, then of course you plan your approach. How am I going to proceed? Well, I'm going to take the mass that's stated in the question, take the volume stated in the question. I'm going to divide the mass by the volume, and I'm going to get the density because finding the density is my goal. So what is my goal? Where am I starting from? How do I get from where I'm starting from to my goal? And then simply carry out the procedure. One of the most common techniques used for solving chemistry problems is one called dimensional analysis. The fundamental idea of this is the answer has to have the appropriate unit. If you're looking for a mass, you would not do a calculation that gives you a volume. You would do a calculation that finds you a mass. So simply being aware of what units stand for what kind of values can help you when you have certain units in your question description. You can then ask yourself, how do those units fit together to get me a unit of that I want for my answer. So if I'm looking for a volume and I'm given some numbers that have units of length, then I realize I've got to take those units of length and somehow cube them or get them to the third power before they become units of volume. If I have grams per milliliter and I want grams, well, I've got to find some way of taking grams per milliliter and multiplying by milliliter. So this is called dimensional analysis. In Chem 1, we call it the factor label method, but it can be used in a more expanded way than simply converting units. What you're doing is you're manipulating units. You're taking the units and using them to solve the problem. If you want to get from inches to centimeters, you would take, as we see at the bottom here, 4.5 inches, multiply it by 2.54 centimeters over 1 inch, and I would get 11.4 centimeters. You might notice there's actually a mistake here. The answer would be 11 centimeters because 4.5 inches only has 2 significant figures. So be aware that you also have to not only solve the problem to get the proper unit, but you should in fact round off the answer to the appropriate number of significant figures based on the previous slide. In fact, this answer here is not rounded yet to the proper number of significant figures. The final answer should be 11 centimeters. All right, so factor label is used throughout all of chemistry. People with PhDs in chemistry doing major research are still using factor label and dimensional analysis. So learn the technique and it will serve you well throughout the whole year. Temperature is a quantity that is often measured in chemistry because it gives us an idea of the kinetic energy of the molecules that we are working with. Temperature often comes in 3 temperature scales: Fahrenheit, Celsius, and Kelvin. In the laboratory, we probably shouldn't be using Fahrenheit since that's an English unit, but occasionally it does crop up. So be aware that there are mathematical formulas for converting one unit to the other. The Celsius has a 0 at the freezing point of water, whereas Kelvin has a 0 at the absolute 0 coldest temperature of no molecular motion at all. And so they although they have the same amount of temperature equals the same number of temperature units, they have a different starting point or 0 point. And so Kelvin is Celsius plus 273, or Celsius is Kelvin minus 273. You might compare some numbers on the temperature scales picture and see that that is in fact correct. Fahrenheit takes the freezing point of water to be 32, so it also has a different 0 point than Celsius. And it takes the boiling point of water to be 212, whereas on the Celsius scale it's 100. If you take 212 minus 32, that's actually 180. If you take 100 minus 0, that's 100, and so 180 over 100 is 1.8. 1.8 is, in fractional form, is 9/5. And so we have this fraction, 5/9 or 9/5, that is used to convert one unit to the other. We also have to add the plus or minus 32 to the equations to show, to account for the different 0 point. Try 1.11, 1.12, and 1.13 in the book to practice converting units of temperature, Celsius, Kelvin, and Fahrenheit. Another important quantity often used for identifying a substance is density. Density is when you take the mass and divide by the volume. So often with solids and liquids, we do grams per milliliter for a liquid, grams per cubic centimeter for a solid. With gases, we often do mass as grams and volume as liters, so grams per liter for the density of a gas. And so density is used often in chemistry to talk about just, how concentrated is the matter, how close and how heavy are the particles in a given certain volume. Another way density can be used is, since the density changes with concentration, it can also be a way of finding the concentration of a particular volume of liquid. So salt water from the Great Salt Lake has a different density than salt water from the middle of the Pacific Ocean, because the degree of salinity or the concentration of the salt is different. Try example 1.14 for practice on density. And finally, we are wrapping things up here with the different ways that chemists classify matter. Of course, matter is anything that occupies space, in other words, has volume, and has mass. The typical three states that we find on Earth most of the time are solids, liquids, and gases. Below, bottom, middle here, we have a diagram showing that in a solid, typically the particles are in some kind of pattern. In a liquid, they have more random arrangement, but they're still packed pretty close together. As you can see, solids and liquids have very similar densities to their particles. And then in a gas, the particles are farther apart and not connected by attractive forces and moving more rapidly than they are in a liquid or a solid. The bottom left-hand corner shows the organization of matter. Notice it starts out as matter as can either have variable composition, in which case it's a mixture, or not variable, or composition that is defined. In that case, we call it a pure substance. This would be what we would call a dichotomous key, because we're asking yes or no questions to get to the next level of classification. A pure substance can either contain various types of atoms, in which case it's called a compound. Typical compound would be water. Water does not have a variable composition, but it does have more than one type of atom. Or it could be have only one type of atom, in which case we call it an element. So copper is an element. Copper does not have variable composition, but it only contains one type of atom. Now, compounds can be broken down into elements. Compounds can be split into elements. You can split water into hydrogen and oxygen, but only by a chemical process. So it has to be a chemical change to separate a compound into an element. I cannot take water and make hydrogen and oxygen by using a physical technique. I have to use a chemical technique which changes the water into hydrogen and oxygen. Elements then break down to the most fundamental particle of matter, which is the atom. If we do have variable composition, it's called a mixture. Now, some mixtures are very well mixed. They're homogeneous mixtures. You visibly cannot distinguish the parts. Once you mix the pigments in a paint and you mix it up really well, it's homogeneous. You can't see that there was once a drop of blue pigment in a white bucket of paint. It's been well mixed. Many mixtures we come across in the real world are heterogeneous mixtures because we can tell the different parts. I can look at a piece of wood and see dark and light grain on the wood. I can look at a rock and see crystals of one color and crystals of another color. So those are called heterogeneous mixtures. Mixtures can be separated into their different materials using physical means. So mixtures can be heterogeneous or homogeneous. They can be separated in pure substance by physical means or physical changes. We see over on the right 3 common techniques that are used to separate. One takes the size of particles and separates it by filtration. And so having a filter paper, you can collect the larger particles in the filter paper and the small particles of liquid go right through. Another one takes advantage of maybe different strengths of intermolecular forces by boiling away the particles that have the weaker intermolecular forces. Then you can collect them by condensing them in a condenser, and that's called distillation. Another one that uses intermolecular forces is separating different colors of dye or ink using chromatography. With this, we are taking advantage of the fact that some of the particles of ink, some of the different colors of ink, are more attracted to the solvent. In this case, it looks like it's probably water. Whereas the other particles are more attracted to the molecules in the paper or the stationary phase or the stationary medium. So if the particles are sticking strongly to the paper, the water travels up the paper but is not able to drag them off the paper and move them upward. If the particles are not sticking to the paper but sticking to the water, then the water moves upward and then takes the particles with them. And so we're able to physically separate the particles into different areas of different color by using their degree of affinity to water or to the solvent or to the stationary medium, the paper. Once we've separated mixtures into pure substances, those pure substances are going to have a constant composition. They can be elements or they can be compounds. Compounds can be separated into elements by chemical changes because compounds have more than one type of atom. Elements are already only one type of atom, and so they can't be separated by any kind of chemical or physical technique. Well, that concludes our first PowerPoint, and I thank you very much for your attention.